let's start. Yeah. Now let's start our talk on the singular line theory meets a Newton polyhedron. Yes. This talk's overview is here. At first, the review of singular line theory, and next the resolutions of singularities and its contents. And thirdly, the Newton polyhedron definition and the theorems. And next, the evaluation of running coefficients using the Newton polyhedron, and last, the proof of concept, the transformers running coefficients. I'll explaining. Yes, and at first, this is very briefly the singular running theories review, the recap. And as you know, the singular running theory tries to evaluate the running coefficient. Running coefficient is the most important value in the singular running theory because by evaluating or by tracking the local running coefficients, we can understand, we can know the models, the characteristics. For instance, the transformers characteristics, when the model grasps new concepts. And so we'd like to evaluate these running coefficient, especially the global running coefficient. However, the evaluating global running coefficient had some problems. It's extremely hard things on the realistic models, like transformers or deep learnings. So today we'd like to show some new methods to evaluate the global running coefficients. And at first, why resolutions are unsatisfactory? I mean to evaluating running coefficient, it needs to use resolution of singularities. It's as you know, the Hironaka's theorems. But it's impossible to construct for any realistic models. As you know, it's too hard things, tough things to find the good resolutions of singularities. And even if the toy models, even for toy models, it's very difficult to construct the good resolutions. And yes, so actually we couldn't use this way the resolutions to adapt the realistic models. So we'd like to introduce the new method to evaluate global running coefficients. So I'd like to introduce the Newton polyhedron. This is a brief definition of Newton polyhedron. The let K means the K divergence, and SLTs are objective functions. Be a real analytic function defined on the open neighborhood of the origin in the Euclidean space, and denote by the K hat, the Taylor series of K as the origin. origin means the global optima. And yes, let's think that situations. And then we can define the Newton polyhedron of K. Large K is an integral polyhedron. The gamma K means Newton polyhedron. It's the convex head of the set U. This is a definition. But if you are a mathematician, you can understand well, just read this definition. But I studied physics. I'm not a mathematician, so I'd like to understand this concept by using illustration or examples. Yes, and yes, and for example, let's consider these types, the K divergence, large K, and just the polynomials. Yes, and then if we get the description of large K by using its parameter, then we can calculate its Newton data. Newton data is a higher order derivative. It means, for instance, the partial derivative. Let's calculate the partial derivative, and this function K has two variables, the W1 and W2. Then for on the W1 partial derivative, it's zero derivative, and on the other hand, the variable on variable W2, let's calculate the 10th higher order derivative. And if this value is not zero, you can draw the point on this abstract space, the 0 and 10. Yes, you can draw the point. And okay.
What was the 10th order derivative again? Is it just you take the partial derivative?
Yeah.
Okay,
Partial
okay.
derivative. Yes, at on some point. Yes, and you can draw both with and this blue rectangle, and next, you can calculate these higher order derivative, partial derivative, and you'll find this value is not zero. So then you can draw this point to yes, and also you can draw this rectangle, and yes, and you can continue the process to the end. And this is Newton data. So Newton data is a partial higher order derivative, and its value is not zero. It's not 0 point. Is a Newton data, and then you can draw the point in this abstract space.
So when you draw this curve, then you compute the
higher order derivative.
The derivative at 0 10, right? Then you move to the right and compute the derivative for 1 10, and then you move until you find something that is not 0, and then you move down. Is that correct?
Yes.
And then and that way you move kind of first to the right, and then you move down, and then to the right, and then you draw that.
Yes.
Okay.
Exactly. Yes. And yes, we can draw another line. Yes, this red dot point dot line called the Newton phase, because this area is Newton called the Newton polyhedron, and Newton polyhedron is convex polyhedron. So this Newton phase is a lower phase of this object. So at first you should calculate. You need to calculate gather the Newton data, and you draw the some points on the this space, and so you will get the Newton polyhedron, and so at last we got the two picture of Newton polyhedron. This is a Newton polyhedron, and this red line calls Newton phase. And then surprisingly we got the global learning coefficient. It's really surprising things. We can calculate this Newton distance dk by using just elementary techniques to calculate the distance. Yes. So for instance, this case, the dk will be 10/3, and the learning coefficient. I'd like to state that the Newton distance is not the origin and Newton phase, the intersection point. It's not a Newton distance. This is not a Newton distance. Newton distance, the distance is the 10 root 2/3 is this distance. On the other hand, the Newton distance is a projected value to the axis. This is a definition of Newton distance. Yes, and so you can draw the diagonal line on this space, and you can find the intersection point, and you will be find the Newton distance by using elementary geometric techniques. Yes, it's very simple, and this is very important theorems to our methods. The Arnold and some the very famous mathematicians that names theorem, and at first I'd like to explain the plain definition to use these theorems. And let's consider the real analytic function k, large k, is non-degenerate. This is a very important state. Over the R space that we do. Okay. The respect to the Newton polyhedron gamma, if for every compact phase, small gamma of gamma, I mean the compact phase is some good it good has character of the Newton phase. So most close to the origin point, the Newton phase called the compact phase. Yes, and so gamma. So then the large K gamma can be has some expression that these like and polynomial form, and this function satisfies the nabla K gamma will be not zero. This is a pre-definition to use this theorem. Then the partition function z, large z, we can draw the equations, and it has an s. It means the pole of the functions. Then by calculating the Newton distance and the pole, the largest pole, and the Newton distance has these relationships, this formula. So S equal minus largest learning coefficient lambda 1 equal lambda 1 over dk. So you can evaluate the learning coefficient by using very elementary geometric techniques. Yes, so I think the junior high school students can evaluate the learning coefficient sometimes. Yes. Yes. So this is another picture of Newton distance. The Newton distance can be described as this. So Newton distance has information on the largest pole, the nearest pole to the origin point. It predicted by the theorems, Marchenko's theorems, predict that. And this is a recipe or procedure to evaluation of the learning coefficients using Newton polyhedron. Firstly, let's find the W0 such that the large K W0 equal to 0 and nabla K W0 will be 0, and let's compute the higher order derivative, I mean the partial derivative combination for any combination of parameters of large K at the global optima. But global optima is not a single point, that is a singular point set, the W0. And next, the Newton polyhedron drawn by the collecting Newton data where the higher order derivative is non-zero. Let's gather the Newton data by calculating the higher order derivative. As you know, as you assume that it's tough thing. It's not easy things, but we can do that. And thirdly, draw a diagonal line on some space, abstract space, starting from the origin and measure the distance between the point, the intersection point, or the diagonal line that intersects the Newton polyhedron face, and the origin. And lastly, the Newtonian distance dk is not the I state that. So the length of the projection of this line onto the respective coordinate axis is the Newtonian distance. So you will get the Newtonian distance, and you will also get the global learning coefficient. It's for me it looks a bit magical things. It's really interesting phenomena, mathematical phenomena. Let's recap the procedure to evaluate the learning coefficient, global learning coefficient. At first, you will get the parameter description of the large K at some point, the global minima, and next you need to collect the Newton data to evaluate, to calculate the higher order partial derivatives, and next, and you can draw, you will draw the Newton polyhedron by using the elementary global geometrical techniques, and you will get the Newton distance, also the global learning coefficient. And then this is a theory yes. So I'd like to demonstrate the great theory by using the great theory. I'd like to demonstrate a proof of concept. So I'd like to evaluate the transformers learning coefficient. At first, consider the ODE model of transformers. And some people know this model, the ODE type of the deep learning models. And on this formula, T is not mean the time, like the physics, the equation of motion, and this T means layers means. And so this formula shows us its meaning. The some layer at T has some input vector. It called can be write the xj. This is a token vector, and this vector is not a single, and it might be has a many number of the vectors. So for example, we will be put some prompts to the transformers. The first words, the second words, third words. Each word is translate to this token vector.
So I asked a question about the relation between the Newton polyhedra and the RLCT. So I know from Xiaowei Lin's thesis and earlier work that under some conditions you can compute the RLCT in terms of Newton polyhedra.
Yes.
You're claiming this without any conditions?
Yes. I assume
Oh, you assume so? Okay.
I assume that you know where this the techniques and its the programs. Yeah, I assume that so I tried to find the very good condition to adapt that theorem. Yes. So I believe that we believe that these kind of formula or models can be adapted the theorem. Yeah. Yes, and so firstly, let's consider these types of differentiation equations, and then we can understand the transformers like ordinary differential equations, ODE. Yes, those formula, these types of formula, and also this parameter. The operator P is a projection operator, and this operator, projection operator, translate the vectors like this. It means the vectors put onto the hypersphere. So this model insist on this model, the token vectors couldn't move out of hypersphere. They can move only on the hypersphere. It's a constraint of the model. This constraint has a very good characteristic to adapt this theorem to evaluate the learning questions. And yes, so as I said, the T-layer output of transformer that can be drawn that, and the vectors difference that can be described that the xi t plus dt means the next layer's output vector, and is the before layers the ice vectors, the xit, and the projection operator, and some translated vectors. And translated vector zit means this equations. And then let's adapt to the singular learning theory, this model. Then we can draw our model by using the P, probability density function P, and X is an input to the T3 years input vector Xi, and T3 years output vector that we can draw, we can use the YIT vector. This is an output of T3 years transformer. And the model, as you know, has a parameter WT. Yes, then we can draw our model's probabilistic density function like that. And also, we can draw the true model. We assume that the true model is in the parameter space. Then we can draw the true model by using some optimal parameter. And then we can evaluate the stochastic free energy. It means just the logarithmic, the log function. It means the gap of the true model and our model. And this has a very pretty form, the Gaussian form. So then the stochastic free energy can be described. Then, this is an original model described paper, and yes, mathematical perspective on transformers. Yes, and I create the new code to product these animation, and so yeah, you can see this is a two-dimensional case. The three-dimensional case. So all token vectors can be moved on just the three hypersphere, the two-dimensional hypersphere. Then all token vectors, the convergence, the some points, and finite numbers, the convergence point it has. And the paper, the mathematical perspective on the paper, transformers, they proved these type of the transformers has a convergence point, the finite number of the convergence point. And yes, and also we can evaluate the stochastic free energy. Then after that, also we can evaluate the large K to compute like that, and then this term. I'm sorry, I forgot the detailed description. This delta means the gap of the two teach labels the vector and the model's vector's gap means. And it also has all normal vector and velocity vector. The dot x vector. The both has gaps, the model and true model, the gap. Then we can draw the formula like that. And then let's consider the inner product. Sorry, the inner product. Let's consider the inner product. We can use a very pretty relationships because velocity vector and normal vectors inner product is then must be zero because all vectors couldn't move the out of hypersphere, they can move only on the hypersphere. Then the velocity vector and point vector has a zero inner product. Then the Kähler divergence large K will be has a very simple form. The 1 minus the ice number of token vector and through teach level of ice number token vector. Yes, very simple formula. Then we'd like to want the expression of a parameter of the large K, and this is a very simple toy model. However, on the other hand, it's still extremely tough things to evaluate the large K. So we assume that these assumptions, the large Q top and large K, the inner product will be large V, the equivalent, and large VT didn't depend on the layer number. So this is a constant the matrix, parameter matrix, and also it's the diagonal matrix. So very simplistic the situations that we assume, and then the transformers, the ODE, will be translated to the more simpler form like that. Then and let's consider the limit, the time t, the t layers level to the infinite plus infinite.
So
sorry?
I ask, in what way do the tokens interact at all?
Even if this toy model is so simple, however, each tokens interact on this hypersphere. Yes, because this constant matrix. However, this constant matrix, the mixing the different level of token vector by calculating these summations of the vectors. Yes, especially the J summation is a mixing the other tokens interactions, like a physics model, on hypersphere. Then we can get this simpler formula. But it's even the tough things, and this model has the hyperparameter beta, the inverse temperature. If you change the inverse temperature, the convergence point will be changed. The number of convergence points, the change will be changed. Some lower number of some high temperature situations, the convergence point will be tend to be a single, and the fewer. And on the other hand, if you set the higher number of inverse temperature, then you will get the a lot of number of the convergence points. This is very simple case, the single convergence point and two convergence points.
Sorry, question. Is this an empirical observation or is this a theoretical?
Yes, this is an empirical the animation, but a mathematical perspective on transformers. The paper proves that these type of transformers, so I mean the constant matrix types of very simple transformer has a finite number of convergence points on hypersphere.
I mean the fact that as you change temperature, the number of attractors changes. Is that theoretically also true?
Yeah. Theoretical true. For instance, yes. This paper shows the phase transitions diagrams on this model.
Next
It
slide.
has a very pretty picture. I'm sorry, please 10 seconds, please.
Yeah, thank you.
Yeah, thank you. Yes. This one. And the vertical axis means value of the inverse temperature, and the horizontal axis means the teeth radius depth. And if you change the value of the inverse temperature, the convergence point, the changes, the 2, 3. Yes. So it depends on the inverse temperature and depth. Yeah. Model's depth. Yes. Yes. Yeah. Thank you. And yes. Continue. Yes. So, and our simulation is at first randomly set the token vectors on hypersphere. In this case, they're just a 3 dimension, and each vectors interact with other vectors, and they will be convert the sum points on hypersphere. That in this case, it has a 2 convergence points. Sorry, this slide is really messy, not beautiful. I'm so sorry. But to derive the K divergence, the parameter expression, it's really tough things. But yeah, we can evaluate the expression by calculating those computation. And I'm so sorry. This is not beautiful, messy slide. I'm so sorry. But as I said that this large K at a limit of the infinitely deep transformer case, the infinitely depth, the last output, the large K will be equivalent that this very simple formula. But I just set a very simple assumption that through teach level that we can set the freely. So the 0, 0, 1 is a teach level. I assume that. Then we can get this formula. And in this case, I set another assumption that it has only 2 convergence points. Then we can set the 1 convergence point to the minus 1 over square 3, the 1, like that. Then we can get the token vectors parameter expression like that. Then the 1 minus a1, the third part is can be expressed like that. Then we can calculate the large case, the collect, gather the Newton data, and so we can draw the Newton polyhedra by using the theorems, the ideas. Then, so as you know, the calculation is very hard. So I used the mathematical and SciPy. Yeah, but it can you can do that by using those tools. Then I found at least the Newton polyhedra is larger than it has a larger order derivative term, not zero. So the Newton distance will be over the 4 over 3. It means these case of the transformers running coefficients will be smaller than the 3 over 4. I mean smaller than 1. So these types of the transformer is a singular model. So we can evaluate, understand by using those tools.
So can I,
Yeah. Yes.
If I remember correctly, so the learning coefficient is always, I mean, even without a this generic assumption, it's always less or equal.
Yes.
So even if you don't know that this model is generic, you get this upper bound.
Yes. Unfortunately, I confirmed this Newton distance over the 4 over 3. I just confirmed that things. But as you state that it might have a probability, the possibility of it hasn't degenerate the points on the Newton phase. But I didn't check the.
Yeah, even I'm saying that if you just want an upper bound, it's not a problem. It's not necessary. Because lambda is always less or equal than 1 over the Newton distance.
Oh, yeah.
Even if with no assumptions.
Okay. It's good news. Yeah.
So like talking about bounds, like how good are these bounds compared to just looking at the Hessian or something? Like how much more do you get from looking at the Newton distance than you get from looking at the Hessian?
I mean, they're certainly quite a bit better than the Hessian, but they are not. Well, maybe.
Yes.
Okay.
Yes. Yes.
The answer is it depends a lot on the model.
Yes. You're right. So yes. You can find the adaptive model. If you are very lucky, then you can find it. Yes.
And maybe if I could just make one point about this. So by definition, right, this Newton distance depends on the choice of coordinate.
Yes. You're right. Yes.
But then you can ask if I make a change of coordinates. So it's always an upper bound for any choice of coordinates. So then you could say if I make a choice of coordinate, can I get the exact value? And the answer is in 2 dimensions it's yes. Like if you just make a simple algebraic change of coordinate, in 2 dimensions you can. In higher dimension you have to do some kind of resolution. It's some kind of change of variable which is more like a resolution of something.
Okay.
But
Yes, thanks.
Yes, but as you state that it depends on the coordinate. Yeah, but on I read something on the learning coefficient is an invariant, the kind of invariant. So why it depends on the coordinate? It's confusing things.
If it's equal, of course it cannot. But if it's an up or down.
I got it. Yeah, thank you. I got it. Okay. Yeah. Then this evaluation method depends on the coordinate system. Yeah. Yes. but and yeah, I think the constraints of the tokens movement space, the only on the sphere, hypersphere, is very good constraint to calculate these terms. So we can expand our trial the calculation to the other models, like neural ODE or other type of the differentiation types, the deep learning models. So, but yeah, as you know, even if this simple case, the calculation is really tough. So, yeah, as I attend this conference, I learned the local learning questions is a really good tools. Yeah, absolutely. Oh. Yeah, yeah. So yeah, I'd like to mix the ideas to evaluate the Newton distance by using by evaluate the expectation value of Newton data. Yes, to evaluate those equations. Yeah, we can use the expectation method, like local coefficient or the SGLD types, the evaluation. Then we can estimate the Newton distance, the local Newton distance by using those methods. Yes, but it's yeah, I don't never tried from now. Yes, that's all I'm saying. Yeah, yes, that's all my talk. Yes. Yes. So yeah, like this simple case, yeah, we can get the parameter expression of the transformers large K. Yes.
Question. I have a question. I think I missed something. The RLCT bound you get, the Newton polygon you get at the end that you showed that is it for t equal to infinity, or is it for a particular layer? Is it for a particular t?
Yes, and particularities and learning questions evaluation is more difficult.
So it's t equal to infinity?
Yeah,
okay.
Infinity is more
so it's using that one.
I'm sorry, yes, you're right. This computation calculation is the the infinity case.
Okay,
yes.
cool.
Yes.
Got it, thank you.
Yes, thank you. And some people in this room might know that
I'm not sure if I'm thinking the same.
okay. Yes. Yeah. The Japanese mathematicians try to generalize the Parchenko's theorem to adapt the many class of the functions. So we will be adapt the theorems the more general, wide the case of class of functions in the near future. Yeah. I'm sorry. Yeah.
Sorry, I came late, so I didn't see which paper you were. What was the other paper you were showing?
In prep, just writing.
Oh, that's your paper.
Yes.
Okay.
Yes.
So I'm familiar with some paper that's talking about neural collapse at the end of the training.
Neural collapse.
Where it's a sort of similar idea where the tokens sort of collapse into sort of groups.
I see.
Of course, it's very natural from an SLT perspective to think that neural collapse corresponds to increasing learning coefficient. So it would be very, obviously in your animations this sort of happens, I guess. But
Yes.
It would be very interesting if this could be related over the course of training to it.
Yes. Sometimes the particles, the orbit, the cross the convergence point. Yes. Yes, it's kind to the phase transitions phenomenon. Yes. Yes. Yes.
Maybe a practical question.
Oh, yeah.
Did you so this is a specific transformer model. But obviously there's a lot of things you can vary, like the number of heads and layer, number of the QK matrix sizes. So is the calculation for the RLC upper bound automated somewhere so that we can implement it?
Yes. Yeah. You will evaluate by using those methods, but it depends on the formulation or the equations the formula.
Okay, so
form. Yeah.
I guess my last thing is there like an upper bound at the end? Do you have a formula for us?
Yes. It could be, but yeah. How? Yes.
That's okay. I'll wait for your paper.
Yes. Oh really? Yeah. Very interesting. Yeah. Yes. After the tell me the idea to the case.
It will be interesting for us to estimate LLC and compare to that.
Yes. So yeah, I'd like to generalize, expand our method to the evaluation for the local coefficients.